Okay, it is noon, so I'm going to go ahead and get started. Looks like we have about 15 people online right now, and we think we had about 45 RSVPs, so we should may have a few more popping in here and there, but I do want to get started. So thank you to everyone who attended today. I know it's been quite a while since you've seen a technical presentation from ISA New Orleans. The last one we did was March of last year. So I'm glad that we finally were able to kind of get things kicked back up. And appreciate you attending, even though I know many of you are probably suffering from Zoom and Teams fatigue as I am. But we'll need to kind of continue on this mode here for a little while, and hopefully sometime very soon we'll get back to live meetings and maybe even a symposium and tabletop type thing. So we're looking forward to trying to get things rolling here with ISA New Orleans section. A few things before we get started. This will be recorded, so Wayne's going to start the recording for the session. We archive these sessions, so you can come back and watch it later, or if you have colleagues that missed the presentation and think it might be beneficial to them, you can point them to our website. They can pull down the archive. We will also PDF this presentation and pop that up there in the archive as well. So if you just want to pull down the PDF of the presentation for collateral for later or to share with a colleague, feel free to do that as well. Other housekeeping rules, just please keep your mics on mute right now unless you have a question. So if you have a question, you can unmute your mic or raise your hand, and feel free to speak. But otherwise, keep the mics muted. And I do want to mention a couple other things. We will give out PDHs for this one for anyone who needs them. We forgot to put that question on the registration link. So if you're in need of a professional development hour, this will qualify. So just send me a note at the end of the presentation, and we'll put you on the list and get you a PDH for your records. I also do want to just mention that we have some guests on the line here. So we took this presentation and we also offered it up to invite the Baton Rouge section to attend. So we have several members from the Baton Rouge section who are attending this session. We also offered it up to the Bluebonnet section, which is Austin, Texas. So they're on. And some members from our greater Lake Charles sections are also on the presentation as well. So so glad to have everybody here, and look forward to getting started with this. So the topic for today is ISA 71.04, the 2013 version, and it is a very timely topic in my world. It's something that I've seen and been struggling with here for a little while, and it's kind of seen an uptick in corrosion and specifically their effect on electronic equipment. And so we're going to go over that. So the content for this presentation is pulled from various sources, but I do want to mention Chris Muller, who's with Purifil, pulled some very good content from some of his presentations. Chris is actually also the chair of ISA 71. So he chairs the committee and then oversees the 4 standards that are coming out of that committee. So we'll go over that a little bit here in a minute as well. All right, so there we go. All right, so this presentation is sponsored by the ISA New Orleans section of the Reynolds Company and Purifil. All right, so first we'll talk about the ISA 71 committee in general. So there is this, as you all may know, with ISA, there are various committees that get formed. There's committees, there's divisions, there's sections, and then committees can build standards. So the ISA 71 committee was formed to promote guidelines for environmental conditions for industries, and I'll show you a little bit about that. So those of you that may be familiar with ISA, and probably it's a good time to do a little commercial for ISA. If you're not a member of ISA, you should consider being a member. as a member of ISA, you get access to all the standards. So the standard we're going to talk about today, this ISA 71.04 that I pulled up on the screen, that's a standard that you can actually view as a member. So you have access to all the ISA standard as a member of ISA. It runs $130 a year, and there's another new feature in ISA, and that is this community called Connect. So ISA launched a social network of its own in August of last year, and it's called Connect. So as a member of ISA, you have access to go into Connect, and you can participate in technical discussions. You can join divisions, post questions, and subject matter experts can answer questions. You can position yourself as an expert to answer questions or participate in presentations. So there's a lot of good engagement that we're getting out of ISA lately, and this Connect platform is very exciting. You can again search out members of like interests, and one of the things that ISA has done just this past year is in the past, your membership for ISA, when you were a member, you could be a member of two divisions. They have opened that up now, so you can be a member of as many technical divisions as you like now with your $130 membership. So if you want to join all the divisions, you can do that. So you can join as many as you like, and that puts you on their mailing lists for their content. You can access their members, access the libraries of information. So very, very useful thing with this ISA Connect. So just another member benefit. Jump back here. So that was my brief commercial on why you should join ISA. So please consider that. So the ISA 71 standard that we're going to talk about today, or the 71.04, is actually one of 4 different standards. So 71.01 was related to temperature and humidity. 71.02 was related to power quality, and then 03 was mechanical influences that you may have to consider, and then the 71.04 is the airborne contaminants. So we'll talk a little more about that. So to give the history behind 71.04, currently we're at the 2013 revision, but it initially came out in 1985, and it was really set up to look at the airborne contaminants that were affecting industries. And someone can correct me if I'm wrong, but it appears to me like the main industry that was calling for this in 1985 was the pulp and paper industry. So any of you all have been in a pulp and paper facility know that there are some highly corrosive gases present, and electronics can take a beating, and even electrical equipment, things like a motor control center the copper can degrade based off of the corrosive gases that are in the environment there. So 1985, the standard was born, and it was a way to classify the types of gases that were present and the amount of corrosion that you could expect on your copper as a result of those corrosive gases. This standard was revised in 2013 as a result of RoHS. And RoHS, if you may know, is the, well, I used to always call it reduction of hazardous substances, but actually that is incorrect. It is the restriction of the use of certain hazardous substances. So that was a European directive that came out in 2002 and was implemented in July of 2006. Now, I know as an industrial supplier, we didn't see a lot of this go into effect until, I want to say it was 2016 was kind of some of the cutoff where you could no longer be grandfathered in, and you had to make the decision whether if you had a piece of electronics that was manufactured in a process that used lead-based solder, you had to retool your line and make that device now without using lead. So just going off from memory here, I'm thinking for us that kind of was in the 2016 timeframe. So that's kind of important because kind of seen an uptick in some quality issues or some corrosion issues as a result of RoHS. So RoHS rolled out in 2006 and eliminated the use of mainly lead, but other substances in the manufacturing process. And then these are all the countries that, of course, have adopted RoHS. So this was the goal. The goal was to reduce lead, eliminate lead from the manufacturing process. And lead was used as a way to bind electronic components to other components through solder. And typically copper wasn't left totally exposed. It was usually covered with a coating or with lead so that it wouldn't deteriorate. So, but RoHS had some unintended consequences. So the manufacturing process switched to where most printed circuit boards were now manufactured with a silver dip process. And silver is a little more reactive than copper, and definitely more reactive than lead, which is hardly reactive at all to chemical elements. So as a result, now with electronics, you can see with the silver dip process problems where you have these flowers, they call them, where you have dendrite fingers grow from the silver and can create shorts in some cases or opens in other cases where you're having continuity issues. So with us in the electronics world, we don't like varying resistance, and we really don't like a resistance value going to 0 or infinity. So that was the issue we have here with some of the formations as a result of the use of silver instead of lead solder. So here's the information on the RoHS and reliability. So the silver immersion technique it gives a path for dendrite fingers to form on surfaces. They can get underneath surfaces and then combine surfaces. So you can make opens or shorts as a result of it. And so this is a pretty serious concern. There's one estimate that I read in a paper that estimates that the RoHS initiative conservatively cost about $8 billion industry wide, or just in the U.S. to implement. And the question is, are we going to get $8 billion worth of positive environmental impact as a result of implementing that change? It's a big question. So going back to the ISA 71.04 1985 edition, back then, the only thing you were really worried about was copper reactivity. So you went in and you classified your area as G1, G2, G3, or GX. So G1 being a mild, meaning that your electrical equipment and your electronics could live there without any problem for quite some time. If you had a G2 level, moderate level of reactivity of copper based off of the gases present, you could potentially see some corrosion. So you might want to take that into consideration and implement some form of remediation or prevention of the gases attacking the equipment. Now, if you got into the G3 area, now your probability is getting much higher that a corrosive attack will occur, and then you get above into the GX level where it's severe, and now you're looking at equipment that's specially designed to be able to survive in that type of environment. So it's a very corrosive environment. So all these the reactivity is measured in angstroms. So it's so if you're less than 300 angstroms, you're G1. Less than 1,000 angstroms, you're G2. less than 2000 G3, and then anything above 2000 angstroms is a GX or severe level. So what's an angstrom, you may ask? This guy, he's an angstrom. That is Anders Jonas Angstrom from the 1800s, and he came up with this unit of measure. And angstrom is actually 10 to the negative 10 meters, so it's 0.1 nanometers is an angstrom. And to give you a kind of a reference, most elements, the diameter of the atom in an element is about 1 angstrom. So very tiny. Okay, so 1985, when we were worried about copper reactivity, not so much a big deal. And I'll show you an example here. So here on the left side of the screen, this is actually a report that comes from one of the corrosion analysis where a copper and silver target is put on a coupon and it's put out in the field for 30 days, and then you send it back to the lab and you analyze it and you figure out, okay, how much buildup in angstroms of corrosion occurs on the copper or on the silver. And I'll turn my little handy dandy laser pointer on here, which Wayne showed me about earlier. So here's the copper and the silver reactivity. So you can see from this report, 1985, you'd be good to go, because the copper you'd be in a G1 to G2 level as far as the reactivity of the copper in this particular facility. But you look at the silver reactivity and you're off the charts. You know, they're at almost 3,300 angstroms in 30 days of reacted silver. So, and again, if your printed circuit boards now are relying on silver connectivity instead of lead, you potentially have an issue. And so let's look at this on this chart here on the right side of the screen. So this shows kind of globally across the world, various locations and very typical types of areas that might exist in various locations, and shows you what kind of corrosion you could expect on the copper side. So if you look here on the copper, you're in pretty good shape here. Everything here is ISA G1. So we're below 200 angstroms. 300 angstroms is copper reactivity. So we're below 300 angstroms in reactivity over a 30-day period. So everything looks good there. But now you come over here to the silver column and you look at silver. Right here we're at 1200 in this DC drive room in Australia. So that's a G3 right there. So it's a low end of a G3. Here we're low end of a GX right now. GX, higher GX, G2, G1. So you see down the road here, we've got more of an issue now in this because of the silver reactivity. So as you may know, this is kind of a big deal. All right, but there's more. So it's more than just the silver reactivity. Guess what affects chemical reactivity? Humidity and temperature. So that sound familiar to anybody on the call here? High temperature, high humidity environments. There's been studies that say that the chemical reactions can actually occur twice as fast for a 50-degree increase in temperature. And then that gets even compounded more when you add humidity into the equation as well. So you need to be concerned about temperature and humidity, not just while the equipment is operating, but even, you know, is it being reacted while it's sitting there on your warehouse on your shelf in storage or in transit to your facility. You know, the reaction process could be occurring anywhere along the lines there, from the time the product is made, transported, stored, and installed in your cabinet. So commissioning, you know, doors are left open during the commissioning process, and there's corrosive environment there. Is the electronics being affected at that point? Normal use and then maintenance activities. So sometimes, as we all know, some periodic maintenance may actually introduce problems, because now you're opening cabinets and you're doing work and again providing a path for that for those chemical reactions to occur in those electronics. Okay, and there's even more. So besides temperature and humidity being contributing factors to silver reactivity, now you also have the fact that what are we doing in electronics these days? Running smaller and smaller components at faster and faster speeds that generate more and more heat. So that compounds the problem even more. So all this leads to some unplanned downtime, and the issue is that there's several issues here. One is that the industry standards such as 71.04, I mean, they're not widely known. I mean, the standard's been out since 1985, got revved in 2013, but still not a widely known standard. I would say I get in 28 years of doing this, I think I've seen 2 specs come across my desk that had someone asking for their electronic equipment with a G3 rating or better. I know we have products like that. We do conformal coated products, and familiar with people using those in harsh environments. But but kind of as a general specification, I don't really see that too much. Sometimes problems are misdiagnosed. So maybe you've got a problem with an electronic component and you're thinking, oh, well, they just don't make them like they used to. The quality's gone down on this product. Maybe that's not the case. Maybe it's maybe it is the manufacturing process, but it's due to the way the world is now told that electronics manufacturer how they have to manufacture those components because they can't use lead anymore. You may not know that you've had an issue because again, you got stuff that's been running for many years. Copper reactivity rates were low. You never had a problem until maybe now. Maybe all of a sudden you're seeing some more failures today than you saw 5 years ago. This could be an issue. And a lot of people just don't know they have a corrosion problem. And then on the solution side, there's not one solution. So just like we deal with in the aspect of safety and security, it's always layers of protection. There's no one silver bullet, no one solution that's going to solve all your problems for corrosion. You really have to take a systematic approach and look at all the potential issues and address them one by one. And we'll kind of go through that with this presentation. So first off, who are the industries that are affected? Well, most people on the call here, you're probably in one of these industries. So refineries, petrochemical plants, pulp and paper, which we talked about, kind of the genesis of the problems came out of pulp and paper, water, wastewater, power gen, steel mills, copper mines. They all are affected. One that's not shown on here is the tire and rubber industry. And I know there's, actually, it's my next slide. I'll go through that. Tire and rubber is a very caustic environment. And so here's just a table from a design guide that I had access to for the tire and rubber industry. And it goes through the various process locations and then classifies what you're typically most likely to see corrosion risk-wise in these areas. So the mix area, those are GX. Component preps, where you got your extruders, those are GX. Now you move over into the tire building facility, you're still G2 or G3 here. Curing process, you're back at a GX. Even the conveyor lines are at G2 or G3, or G3 or GX for the cured products. Even you don't get into kind of clean air, if you will, until you get into the conveyors for the final finish area, or in your material handling side. Once you've built the tire and you're storing it in the warehouse, now you're down into a G1 environment. Water, wastewater, kind of same thing based off a design guide here. Here are a few different locations in a water wastewater facility or a water treatment facility, and their levels and what what types of gases are present here. So office space, you're okay. Electrical room, probably all right. Now you get into the headworks and clarifiers. Those are high corrosion environments. Desludging, sludge storage, lift stations, all high corrosive environments. So what's the cost of corrosion? Well, whatever an hour of downtime is for you is what you would figure out. It's going to take you multiple hours to figure out the problem, but we all know about the cost of downtime. In this particular case, pulp and paper mill, craft paper. For them, it's $42,000 plus per hour of downtime. All right, so we've kind of stated the problem. Now, what do you do to fix the problem? Well, there's a three-step process, and it really consists of first assessing your area. So figure out, do you have corrosive gases present in the enclosure or in a building or in an area? And if so, how bad are they? How bad do they react copper, and how bad do they react silver? Next step is to, once you know kind of what you're dealing with, are you dealing with G3 level gases? Are you dealing with GX? Are you just dealing with G2? Based off of each issue that you're dealing with, you come up with a control strategy to knock that level down to an acceptable level, which would be a G1 level. So as I mentioned on that one slide, there's no one silver bullet. And so just like safety and security, it's all about layers of protection. You build several things into your process to protect and control the corrosive gases that the equipment's going to be exposed to. And then once you put your control procedures in place, you need to monitor them. You need to make sure that what you put in place is still holding, and that you don't have, you may have spent a ton of time working on sealing your enclosures up and making sure that that all the penetrations were all nicely sealed. But you got a PM happening and somebody leaves a door open on the enclosure, and so now you're back to square one. So you got to continually be vigilant and monitor the conditions. And the ISA 71.04 standard can help with all this. So the first thing on the assessment side is what's called a corrosion classification coupon or a reactivity monitoring coupon. So as I mentioned before, very simple, low-tech way, low-tech, at least low-tech on implementation and the testing side. All the smart guys in the lab have to give you the analysis. But what you do is you get one of these corrosion classification coupons, or several, and you put them in various locations. So you put them on the return, near the return air in a let's say a drive cabinet that's sucking return air into cool the drive. You may want to put one on that enclosure. Various points in the building. So places where there's airflow, you may want to put one of these coupons. And what you do is you leave that coupon there for 30 days. And then at the end of 30 days, you put all your information on there: company, location, application it's in, the date you put it in, the date you took it out. So all the various information about the application. After 30 days, you put it in a bag, send it back to the lab. The lab analyzes it, and then they generate back to you a report that shows you, what's going on in your facility, and what how reactive copper is and how reactive silver is based off of what's going on. And there are various manufacturers of these coupons. I can think of probably 3 or 4 people that offer these coupons and these services. There are variations to these coupons too. One nice option to these coupons is you can actually get them with a little temperature and humidity sensor button on the side. So while it's reacting the copper and the silver, you're also data logging all your time and temperature along the way. So if you see some high temperature spikes or some erratic humidity changes, swings, high, low humidity changes, you're capturing that as well, and that becomes part of your report. So that's kind of nice. And there's even, let's say you didn't want to deal with the coupon, or you couldn't put the coupon in all these areas. There are some small little go no go monitors, kind of like a fuse that would just sit there and monitor the gases and the reactivity of silver. Once you get above 1200 angstroms, a little green light goes to a red light, and you know, hey, I probably got a problem. And then you can follow up with a coupon after the fact. So here's an example of a report, and actually this is one from our area. So it has been, the names have been changed or redacted to protect the innocent, but so in this case here, here's the copy of the actual coupon that was returned. So the silver, visually you can see the silver doesn't look too bad. Visually you can see the copper doesn't look too bad here on the top. The silver, black silver is not good, so you can tell that's been highly reacted. This is that little temperature and humidity sensor button on this particular coupon, and so this was on an e-house in a location. And so you can see the overall report, this thing came back as a GX class. So the copper was affected by 591 angstroms in a 30-day period. So that would have put it in the G2 area for copper. But the silver, you can see, is almost at 3,300 angstroms in a 30-day period. So that puts it way into a GX level. And it's easier to see here with the graph on the right. So this is actually the same data, just in a bar chart. So there's our copper down here in the G1 low G2 level, and then here's our silver reactivity in the GX level. I grabbed a little screenshot of this is the temperature and humidity data logger. Good news here on this one is that temperature and humidity were both in line. The temperature was never got above 60 degrees C and never below 35 degrees C, and was pretty consistent the whole way through, so that was pretty good. And then, that's temperatures right here. This is temperature is in 20, about room temperature, so about 20 degrees C the whole time. Humidity percentage was kind of floating around 40% humidity, which is not bad for this particular application. So, and we didn't see any wide changes, high humidity, low humidity here. So that all looks out pretty good. But the real problem here with this particular situation is the silver was reacting, and as a result of this this reactivity of the silver, we actually had a variable frequency drive shut down because of the reactivity, and it's because one of the boards on the drive failed, which caused a shutdown. Okay, so once you assess, now what do you do? How do you control it? Well, there are guidelines on this in the standard, and there's several manufacturers out there that have guidelines and recommendations on what you can do. And there are things like looking at your enclosure, looking at your cooling, purifying the air, looking at the construction and how you install the equipment, heating and cooling there, how you maintain it. So kind of the key bullets are making sure your enclosures are sealed, conformally coat your electronics where you can if you've got a corrosive environment, control the temperature, air conditioners, heat exchangers, fans, filter fans specifically, following good installation practices, pressurize your enclosure, or pressurize the room even better that the enclosure is going in. And then there are means to absorb the gas out of the air to an acceptable level through media, through corrosive gas absorption media devices and filters. So we'll cover some of that. So starting with the enclosures, one of the guidelines here is, if you can do a NEMA 12 or better enclosure, that would be a really good start. And even preferably a welded enclosure, continuously welded enclosure of NEMA 12 or better is going to be tightly sealed, and it's going to give you a really good shot at minimizing the amount of gas that gets into that cabinet, especially if your door is closed and your gaskets are maintained. These modular enclosures are still good as well, as long as you've sealed up everything and you've made sure that you've not damaged this enclosure in transit. If this thing gets beat up and bent in transit, that you're not going to get a good seal on the door, and that's going to be a path for more gas to come into the cabinet. All right, here's some nice shots of some best practices. So this drawing here and this picture on the top corner, so you can see everything's nicely sealed. So all the penetrations coming into the cabinet are all sealed up. Right here with cord grips on this one, they're all sealed up as well here. Nice seal here on all the wire penetrations coming through this particular device. One thing to note here is cleanliness. Looking in, making sure that your cabinets stay clean. Because the gas isn't the only contaminant that's an issue. Dust is an issue for electronics as well. So it's always good to keep a clean cabinet and keep the dust down as well. And then you want to keep the doors closed. So if you're going to spend all the time sealing all these devices up, all these cabinets off, you can use a device to keep the doors closed. So if you need to access a drive or a PLC or your control system, there are devices that you can mount on the enclosure that allow you to get access to that network without having to open the door. So those are good to have as well. All right, so the next thing you want to do is you want to make sure that you're looking at temperature control. So whether that's air conditioners on the enclosure or fans, those both can help with temperature control. If you have the chance to use a filtered fan versus a non-filtered fan, please go the filtered fan route. That's gonna give you a better chance at knocking down some of these corrosive gases. And then in your installation procedures, make sure that you don't add to the heat problem by installing your devices incorrectly. So follow your manufacturer's recommendations on proper distances to the top of the enclosure or to your wiring duct and to the sides of the enclosure and from device to device to keep the temperatures down within the normal operating limits for that equipment. And then we mentioned humidity. So humidity is a big issue, especially for us here in South Louisiana. So there are ways that you can help with humidity and its effect on corrosion. And so you can actually put dehumidifiers in the enclosure with a drain, either a stainless steel drain or a non-metallic drain. So that exists. The old tried and true desiccant packets, nothing wrong with a good PM program to use desiccant packets, swapping them out from time to time as they kind of go through their useful life. And then you have corrosion inhibitors, corrosion sprays, so a whole host of products that can help kind of keep that moisture out and keep corrosion from occurring. And then you can also attack this by purchasing products that are suited for or better suited for that environment. So instead of just purchasing a product that was not rated for a hazardous, a corrosive environment, you can purchase products that have been manufactured and tested to the ISA 71.04 standard for a certain level. So you can buy G2 and G3 level products, or G3 plus into the GX level even. So there's pretty much every process control manufacturer out there, PLC manufacturer, all offer some level of protection, and they utilize that ISA 71.04 standard for their testing, and they warranty the products based off of that as well. And what's interesting note here is that there are some new manufacturing processes as a result of RoHS related to conformal coating. So conformal coating today isn't necessarily the same as it was a few years ago. And that's actually my next slide. So let me jump to this one. This is actually showing a variable frequency drive IGBT, power power conductor device. And so we can see a standard IGBT without coating is being reacted and attacked by the corrosive gases in the environment. And you can see those dendrite fingers we talked about that grow on the silver. On this side here is a sealed and protected IGBT that eliminates that dendrite growth, and you don't see the dark areas on the copper like you do on the one on the left. So this was my other point, was the coating itself. So conformal coating today can be different than conformal coating of years past. It's been determined that some of the older spray conformal coating processes still left enough area to get to, and were porous and could crack over time to where corrosive gases could intrude and get under that coating layer. So there have been advances made in the coating process, and some manufacturers do some accelerated testing on the mixed flow gases to make sure that that these new coating processes can hold up to very harsh environments. And then there are areas where you just can't coat. I mean, there's some pieces of electronics like here edge connectors on a board where you need to have metal to metal contact. You need to have continuity. So you can't coat those with a conformal coating, because now you wouldn't have electrical continuity. But for those situations, you do have dielectric grease. So dielectric grease could be put on the fingers of a board, and it will give some level of protection. And so there's a little test picture of a non-treated board and a treated board, and it's just as simple as applying some dielectric grease to that board. And then, kind of like the enclosures, on your electronics as well. If you've got plugs and ports and covers, use them. Don't take those off. Keep them on. If you have unused Ethernet ports, plug those up, or unused connectors or fiber optic ports. Always good to keep the plugs on those things. And then the last thing you can do is actually attack the air itself. So if there's a electrical building or a control room or something where you have an air issue with corrosive gases in the air, you can always attack that as well. So there are many different methods to do air exchanges with that equipment in that room through some sort of media that will remove the corrosive chemicals from the air and get it down to an acceptable G1 level. And could probably do a whole presentation on that in itself, and that would not be me giving that presentation, because I am not a good air conditioner, airflow, air exchange kind of guy. But if that's of interest, maybe we could do a follow-up presentation. But here's just some of the, an example of a scrubber type device. So this is one where you have your outside air coming through a scrubber. So there's some media in this scrubber that's going to absorb the corrosive gases, and the corrosive gases are going to stick to the media. So these are like little pellets that would be in this device. And so as the corrosive gases come through, they attach to the media, and then what comes out the other end is cleaner air. And what's nice about that is the media it's kind of first in. So the media that's closer to the intake is going to get reacted first, and then further on down the line. So you might have media that's used up here, but you have some fresh media here that starts to get reacted. Then you get down to here. So you kind of monitor that media and its effectiveness as the gases flow through it. And like I said, there's a lot of different technologies here, a lot of different types of scrubbers. There's ones that mount outside the building. There are where you need to kind of build that into the design or retrofit them into the building. There are some that you simply put inside the building and you put the media in it, plug it in, and if it's a smaller volume of air in the building, it can actually just recirculate the air inside the building and clean up the gases from the air. So the last piece of it is, so we talked about assess, control, and then monitor. So the last piece is the monitor. So if you're going to take all these, if you're going to determine what your problem is, what gases you have, and what you need to how you need to reduce the problem, you put your control mechanism in place. You work on your enclosures. You work on sealing up all your connections on the enclosures. You potentially utilize some more robust electronic hardware that's harsh, that's been hardened to fight off these gases, and then maybe you've taken some means to even improve the air quality in that room itself. So you've deployed scrubbers, etc., just to knock that corrosive gas down to an acceptable G1 level. So you do all that stuff. You still need to keep monitoring. You need to monitor the media that you've used if you've got scrubbers, or if you've deployed these solutions with your enclosures. You need to monitor and make sure, are your doors closed? Are your gaskets being maintained? Are you keeping the dust out of the enclosures? Just straight visual inspections, just to make sure that that whatever control measures you put in place, they're still working. And then in the case of the gases themselves, so you can continue to monitor the gases. So you could take the approach of just using your coupons, and you could throw coupons out there just to make sure that things are still at an acceptable level. There are electronic devices that can actually measure in real time the reactivity of copper and silver, and can actually tell you the levels and report them out to your control system, and can tell you, when you're at above a certain rate of change. So if you see that you're moving more than 200 angstroms of corrosion of silver in a 30-day period, this would alarm you on that. So maybe everything's all good, but you're doing a PM and somebody's leaving the door open on the control room, and then all of a sudden you see a spike for like 1 or 2 days of the preventative maintenance. A unit like this would let you know that's happening, whereas you might miss that if you just use you would miss that if you use one of these coupons, because this is looking at a 30-day period. This is real time. And then, as mentioned before, you got the small little go no go sensors. So once this thing sees more than 1,200 angstroms of reactivity of silver, it gives you a red light and says that you've got a high level. Monitoring is also important on the case of the media. So if you've deployed scrubbers, you've got media in these bins or these beds that you need to make sure it's fresh media and can do its job and remove the gases. So there are silver rods that get inserted that you can kind of like a dipstick, kind of check and see is that device still doing its job, or does it have half of the media left that's still able to react to gases, or is it only a third left, or is it fresh? And there are even electronic bed monitoring systems to monitor this instead of the dipstick route with a probe that you would put in here and electronically monitor how well this media is doing its job in removing the gases. So in summary, there's really a 3-step process for corrosion control. You've got to assess first, so you got to determine what types of gases are present and what levels of corrosion you're seeing on copper and on silver both. And if you're going to have a problem, more than likely it's going to be on the silver side first. Yeah, so you have to assess the area, figure out what you're dealing with. Then you put in your control measures. So figure out what you need to do to make sure that those electronics are only being exposed to G1 type air if possible. And if not, use electronics that are suitable for G2 or G3 or even GX. environments if that's what you have to do. And then monitor. So you put your controls in place, but you still need to keep monitoring to make sure that the controls you put in place are doing the job and you're still protecting your equipment and preventing unwanted downtime. And with that, we've got about 10 minutes left, so I will open it up to any questions anyone may have. Looks like we got about 29 participants there online right now. So, if anybody has any questions, I'll hold the line. If there's anything that we can do with ISA, any topics you'd like to see, please shoot me a line. Let me know what you'd like to see. I would encourage everyone to go out there and if you're a member of ISA, log into the ISA Connect and accept the terms of use, and then you can participate in these technical discussions. You can reach out to other colleagues and connect to them. There's a young professionals group in ISA as well. So if you're less under the age of 35, you can join the young professionals group and interact with more some of your colleagues more in your age range.
Testing 1, 2, 3. Can anybody hear me? Hello.
And as I mentioned before, we'll take this presentation. We'll post
Testing 1, 2, 3. Can anybody hear me?
I can hear you. Is that Art?
Yeah, I sent you a chat. I didn't know how to ask a question.
Sorry.
I'm an old dog, so I need to be learning new tricks.
That's right. I wasn't paying attention to the chat. So.
All right. Well, first of all, thanks. This was a surprisingly interesting presentation. It was a whole new world of information for me. Appreciate it.
Okay.
A question.
Forensic studies.
Yeah. A question is, are any of these corrosive effects reversible in any way with a liquid or a vapor? Like if the little fingers are growing, is there a way to make them go back with any kind of a treatment?
I do not think so. I mean, if someone else is on the call that knows that better than me, please speak up if I'm wrong, but I don't think so. I mean, we're talking about things that are happening at a very small level. And
this is Kevin Jameson from Fury Air Filtration. No, I'm not aware. Once the damage is done, it's done. And even if you stop the damage just before it's done, as long as damage even continues just a little bit, you can still have a failed circuit. So unfortunately, I'm not aware of any way to undo the damage.
Okay, thanks.
Yeah, the only thing I can think of is in the case of the dielectric grease on the fingers. So if you had edge connector boards and you noticed that they were being attacked, you could go grab yourself some dielectric grease, put it on those fingers, pop the board back in place, and more than likely it would help. But down at the microelectronic circuit level, no, I don't think you got a chance of fixing that. Okay. Any other questions? And
Dean, can you hear me?
yes.
Yeah, it's Rick Albrecht. I raised my hand and I don't
Oh, I
know.
see you. Sorry. Yeah, I'm
Oh,
kind of slow on the uptake when it comes to this chat
You're
stuff.
quicker than I am, so, but anyway. If there are any members from Baton Rouge section, I would just like to thank them for coming and taking advantage of what we'd like to keep going here. And hopefully down the line, as you know, our plans are to start hosting some of these ourselves and inviting both Bluebonnet and New Orleans section to join in with us. So in order to get that going, we're looking for a little bit of help. We have a bare bones board here, and we got a lot of openings. I'll be posting some in different areas, ISA Connect being one of them. So I would urge them to take your heed and or your suggestion, I should say, and get active on ISA Connect, because we'll be doing a lot of our information posting on that source. So again, thanks for showing up and thanks for the presentation. It was very interesting, and I finally know what an angstrom is.
All right, there you go.
Okay.
Thanks.
Thanks.
All right, we'll end it now then. I'm going to stop sharing. Thanks for joining.